The RG-33 mine-resistant ambush-protected vehicle was born not from routine military modernization, but from desperate, blood-soaked necessity during the middle years of the global war on terror. By 2006, the battlefield in Iraq had fundamentally shifted from traditional maneuver warfare to grinding counterinsurgency, where roads themselves became weapons. The ubiquitous high-mobility multipurpose wheeled vehicle, commonly known as the Humvee, a Cold War relic designed for reconnaissance, had proven catastrophically vulnerable to the insurgents' weapon of choice, the Improvised Explosive Device. The flat-bottomed hull of the Humvee acted as a blast trap, catching the vertical energy of buried explosives and transferring it directly into the crew compartment with lethal efficiency. The Department of Defense faced a survivability crisis. Adding armor plates and ballistic glass to Humvees was merely a stopgap that overwhelmed the vehicle's suspension and engine without solving the fundamental geometric flaw of its chassis. Casualty rates from underbody blasts climbed steadily, creating immense political pressure in Washington. Secretary of Defense Robert Gates declared the acquisition of these mine-resistant vehicles the department's highest priority, initiating an industrial mobilization not seen since the Second World War. In this crucible of urgency, BAE Systems, leveraging its South African heritage, brought the RG-33 from concept to prototype in a staggering 7 months. The RG-33 represented a divergence in design philosophy from hurried solutions of the time. While competitors like the international Max Pro utilized a commercial truck chassis with an armored box bolted on top, allowing for rapid manufacturing using existing assembly lines, the RG-33 was a purpose-built monocoque citadel. It was not a truck wearing armor. The armor was the truck itself. This distinction would define its operational life, creating a vehicle that was structurally superior and survivable, yet plagued by the immense weight and complexity inherent in such a specialized machine. To understand the engineering foundation of the RG-33, one must look south of the equator to the bush wars of southern Africa. The vehicle is the direct descendant of the RG-31 Nyala, and by extension, the Caspier and Buffle vehicles developed to counter landmines during the South African Border War. These conflicts pioneered the V-hull concept, a geometry designed to deflect blast energy away from the hull rather than absorbing it. The RG-33 is essentially a scaled-up Americanized evolution of the RG-31, incorporating United States-specific requirements for engine systems, communications, and protection levels. BAE Systems mobilized a global manufacturing network to meet the voracious demand of the military. While the design leveraged South African intellectual property and modeling tools, the physical production was a transcontinental effort. Facilities in York, Pennsylvania, Aiken, South Carolina, Sealy, Texas, and Fairfield, Ohio were activated to cut steel and weld hulls. The scale of this effort was massive, with BAE Systems coordinating a supply chain that had to source high-strength ballistic steel from the limited number of mills capable of producing it. The speed of this mobilization came with costs. The rapid prototyping meant that the vehicle was being fielded, tested, and modified simultaneously. The initial delivery of 4 test vehicles to the Marine Corps occurred in January 2007, with orders following almost immediately afterward. This building while testing approach would manifest later in the vehicle's service life through frequent modernization programs and maintenance challenges. The defining feature of the RG-33 is its monocoque hull. In automotive engineering, monocoque means single shell, implying that the external skin of the vehicle supports the structural load, eliminating the need for a separate internal frame. For the RG-33, this skin is composed of high-strength ballistic steel plates welded together to form a rigid, boat-like structure. The V-shape is a deliberate manipulation of physics. When a high-explosive mine detonates under a vehicle, the expanding gases and shock wave move vertically at supersonic speeds. A flat hull presents a perpendicular surface to this force, absorbing the maximum amount of energy. The floor plate buckles, fragments, and launches the occupants into the roof. The RG-33's V hull presents an oblique angle to the blast. This geometry resolves the vertical force into two components: a normal force perpendicular to the surface and a tangential force parallel to the surface. By steepening the angle of the V, engineers maximize the tangential component, effectively causing the blast wave to slide off the hull and vent out to the sides of the vehicle. This deflection reduces the total energy transferred to the cabin, keeping the forces experienced by the crew within survivable limits. The steel used in the RG-33's hull is not standard structural steel. It is specially treated ballistic steel designed to possess high strength, to resist penetration, and high toughness to prevent shattering under blast loading. The integration of these armor systems results in a vehicle of immense mass. The 4x4 variant weighs approximately 38,000 pounds, while the 6x6 variant tips the scales at 58,000 pounds. This weight is the primary penalty of the monocoque design. Unlike a frame chassis where the steel can be relatively mild, the entire structure of the RG-33 must be high-grade armor, making the vehicle heavy, expensive, and difficult to repair if the hull is warped by a massive blast. A critical survivability feature is the separation of the engine compartment from the crew citadel. The engine bay is a separate module bolted to the front of the armored tub. In the event of a catastrophic mine strike on a front wheel, the entire front assembly, including engine, axle, and hood, is designed to absorb energy and, if necessary, shear away from the crew compartment. This sacrificial philosophy ensures that the kinetic energy of the blast is expended destroying the mobility systems rather than breaching the survival cell. The crew might be stranded, but they remain encapsulated in the armored lifeboat. Moving a 29-ton vehicle requires a power plant of significant capability. The RG-33 utilizes a commercial engine adapted for military service, a decision driven by the need for rapid availability and parts commonality. The prime mover is the Cummins inline 6-cylinder turbo diesel engine, producing 400 horsepower and approximately 1,200 pound-feet of torque. This engine is a staple of the commercial trucking industry. The engine utilizes a variable geometry turbocharger, which adjusts the turbine housing to optimize boost across the rotation range. This provides high torque at low rotations, essential for getting the massive RG-33 moving from a standstill, especially on soft terrain like sand or mud. The engine is cooled by a massive radiator assembly protected by armored grating. However, the operational reality of Iraq and Afghanistan, with ambient temperatures exceeding 120 degrees Fahrenheit combined with low-speed, high-load convoy driving, pushed this cooling system to its limit. The engine is mated to an Allison 3200 series fully automatic transmission. This 6-speed unit is renowned for its durability and intelligent electronic controls. The transmission features a wide gear ratio spread. First gear provides the leverage needed for launch. The top two gears are overdrives, allowing the vehicle to achieve highway speeds of roughly 68 miles per hour without over-revving the engine. The torque converter plays a vital role in off-road mobility. By multiplying torque during the stall phase when the engine is revving but the wheels are not yet turning, it allows the RG-33 to climb steep grades and surmount obstacles that would stall a manual transmission vehicle. Power is distributed through a transfer case to heavy-duty axles. These are planetary hub reduction axles. Unlike standard truck axles where the final gear reduction occurs in the central differential, planetary axles perform a second reduction at the wheel hub itself. This design significantly reduces the stress on the axle shafts as they spin faster but carry less torque. The massive torque multiplication happens right at the wheel, exactly where it is needed to turn the run-flat tires. The hub reduction design allows for a smaller central differential housing, improving ground clearance, a critical factor for avoiding hang-ups on debris or rough terrain. Despite the robust specifications, the RG-33 is underpowered. With a power-to-weight ratio of roughly 13.7 horsepower per ton for the 6x6 variant, acceleration is lethargic. In the mountains of Afghanistan, the vehicle struggled to maintain convoy speeds on steep gradients, often lagging behind lighter platforms. The fuel consumption is equally problematic. The 80-gallon fuel tank provides a theoretical range that evaporates quickly during idle heavy convoy operations or off-road maneuvering, creating a significant logistical burden for fuel resupply convoys. The suspension system of the RG-33 represents one of the most critical evolution points in the vehicle's history. The initial design utilized a standard double wishbone independent suspension. While conceptually sound for ride quality, the components were simply not robust enough to handle the immense weight of the up-armored hull, especially in the brutal terrain of Afghanistan. The RG-33 suffers from a high center of gravity. The V-hull design necessitates that the crew floor be elevated significantly above the axles to allow space for the blast deflector. This pushes the roofline to over 11 feet. When combined with the soft, long-travel suspension required for off-road use, the vehicle exhibited significant body roll. In operational conditions, this led to a dangerous susceptibility to rollovers. Statistics from late 2007 to early 2008 indicated 144 non-hostile rollover incidents. These accidents were not just operational nuisances, they were lethal events where gunners could be crushed or crew members injured by flying equipment inside the cabin. To address the durability and stability issues, the Department of Defense contracted Oshkosh Defense to retrofit the RG-33 fleet with the TAK-4 independent suspension system. This upgrade was transformative. The TAK-4 system utilizes massive control arms and high-capacity coil springs that provide up to 16 inches of vertical wheel travel. This allows the wheels to maintain contact with the ground over extreme undulations, improving traction and braking performance. The upgraded suspension offered a 3 times smoother ride compared to straight axle designs or the legacy suspension. This is not merely a comfort issue. A smoother ride reduces crew fatigue and protects sensitive onboard electronics from vibration damage. The retrofit allowed the RG-33 to travel at higher speeds off-road, up to 30 to 40 miles per hour, in terrain that would have previously restricted it to a crawl. The improved damping control significantly mitigated the rollover risk by keeping the vehicle flatter in turns and more composed during evasive maneuvers. If you've ever seen one of these massive vehicles in person, drop a comment below and tell us about your experience. And if you're enjoying this deep dive into military engineering, hit that like button and subscribe so you don't miss our upcoming videos on other incredible machines of war. The RG-33's modular design allowed it to be configured for a wide array of mission profiles, each with specific engineering adaptations. While the standard 4x4 was intended for urban patrol, the bulk of production was diverted to United States Special Operations Command. The Special Operations variant is the sports car of the mine-resistant world, relatively speaking. It features the TAK-4 suspension as standard, optimized engine tuning for better throttle response, and a suite of advanced communications gear. It is almost universally equipped with the common remotely operated weapon station. This system allows the gunner to remain inside the vehicle, aiming and firing the .50 caliber machine gun or grenade launcher via a joystick and video screen. This eliminates the vulnerability of the turret gunner position, a primary target for insurgent snipers. Recognizing the weight of the armored rear door, the Special Operations variant includes a pneumatic or hydraulic rear door assist mechanism, allowing for rapid exit during raids. The heavy armored ground ambulance variant represents a paradigm shift in combat casualty care. Previous ambulances were soft targets. This variant turned the ambulance into a bunker. The rear compartment is gutted of squad seating and fitted with a litter lift system, capable of loading patients on stretchers mechanically, a crucial feature when lifting a 200-pound soldier in full gear into a truck with a 4-foot deck height. It features an upgraded climate control system with additional fresh air handlers to maintain a sterile environment and prevent heat stress and casualties. The electrical system is bolstered with power inverters to run commercial medical monitoring equipment, oxygen concentrators, and suction devices. It provides seating for 3 medical attendants, allowing a full medical team to work on 2 critical patients simultaneously while the vehicle maneuvers through a kill zone. The medium mine-protected vehicle configuration is the primary tool for route clearance patrols. These vehicles lead the convoys, hunting for explosives. The most distinctive feature is the high-visibility interrogation arm mounted on the front bumper, often called the spork or iron claw. Controlled by an operator in the cab via a joystick console, this hydraulic arm can extend roughly 20 to 30 feet. It is equipped with cameras and a claw or rake. The arm allows the crew to dig up suspicious trash piles, move debris, or inspect culverts from a standoff distance. If the device detonates while being manipulated, the blast occurs at the end of the arm, protecting the vehicle and crew. The arm is considered a sacrificial component. It is cheaper to replace a hydraulic arm than an entire vehicle or a human life. The rear ramp is often modified to allow for the deployment of unmanned ground vehicles like the Talon or Packbot. The crew can lower the ramp, drive the robot out, and conduct reconnaissance without ever exposing a soldier to sniper fire. Operating the RG-33 is a sensory experience defined by confinement, noise, and a paradoxical sense of vulnerability and invincibility. The interior of the RG-33 is cramped despite its exterior size. The walls are lined with spall liners, essentially Kevlar blankets that catch flying metal fragments in the event of a penetration. The space is filled with radios, jammers, ammunition cans, and water bottles. The cabin is incredibly loud. The lack of sound deadening combined with the diesel engine and heavy driveline creates a deafening roar that necessitates the use of the vehicle intercom system for all communication. The smell is a distinct cocktail of diesel fumes, gun oil, stale sweat, and the metallic tang of hot electronics. The crew sits in blast-attenuating seats. These seats do not touch the floor. They are suspended from the ceiling or sidewalls on energy-absorbing mounts or straps. In a blast, the floor deforms upward violently. By floating the seats, the occupants are decoupled from this acceleration, preventing spinal compression injuries. The 4-point or 5-point harnesses are mandatory and uncomfortable, locking the soldier in place like a fighter pilot. Driving an RG-33 requires a fundamental recalibration of spatial awareness. The driver sits high above the road, behind nearly 4 inches of ballistic glass that distorts peripheral vision. The hood is long and high. A standard passenger sedan can disappear completely within a 20-foot radius of the front bumper or the right side door. This creates extreme hazards in urban traffic. To mitigate this, the RG-33 is equipped with large mirror arrays and often retrofitted with camera systems, including thermal driver's vision enhancers and rear-view cameras. However, these systems can be rendered useless by mud, dust, or electronic failure, forcing the driver to rely on the vehicle commander to call out clearances. Entering the vehicle is a physical feat, requiring a climb up retractable steps. The rear hydraulic ramp on the 6x6 is a frequent point of failure. If the hydraulics fail due to a blown seal or electrical short, the crew must use a manual backup pump to raise or lower the heavy ramp. This manual process is exhausting, requiring hundreds of pump strokes to close the ramp, a dangerous delay in a hostile environment. Similarly, the heavy armored side doors require pneumatic assist cylinders to open. If these fail, opening the door against gravity. If the vehicle is on a slope, is nearly impossible for a single soldier. While the RG-33 was a savior for the infantry, it was a curse for the maintenance corps. The rapid acquisition strategy meant that the logistical support was never fully established before the vehicles hit the theater. The RG-33 is assembled from parts from global suppliers. A simple routine service could become a logistical scavenger hunt. Mechanics reported that a standard oil change could require up to 5 different part numbers for filters, depending on the specific production batch and variant of the vehicle. Because the technical data packages were proprietary and the systems complex, the military relied heavily on field service representatives, civilian contractors, to perform maintenance. Unit-level mechanics were often restricted to basic checks, while deep diagnostics on the engine or electronics required a certified mechanic, often a civilian. This created a bottleneck where a platoon could be sidelined, waiting for a contractor to approve a repair. The armor protection makes maintenance physically difficult. To access the starter motor on the engine, a component that fails frequently due to the high compression and the frequent start-stop cycles of patrol duty, mechanics must navigate around blast plates and frame rails. Replacement is not a simple swap. It requires removing other components and working in tight, dark spaces. The hydraulic lines for the ramp and door assist systems run through the armored hull, making leak detection and line replacement a time-consuming ordeal requiring the removal of interior panels and equipment. The learning curve was so steep that the military established a specialized school at the Red River Army Depot designed to train mechanics specifically on the idiosyncrasies of the mine-resistant fleet, teaching them how to troubleshoot the complex electrical systems and maintain the heavy-duty suspension components that were alien to mechanics used to working on Humvees. As the intensity of operations in Iraq and Afghanistan waned, the military was left with thousands of these specialized behemoths. The RG-33 fleet underwent a reset program, particularly at the Letterkenny Army Depot, where vehicles were torn down and rebuilt to modernized standards. This modernization included installing the independent suspension on all models, upgrading the air conditioning to handle higher thermal loads, and standardizing the robotic deployment capabilities. A significant number of RG-33's were declared excess defense articles and made available to law enforcement agencies through the 1033 program. Departments ranging from large metropolitan forces to small county sheriff's offices acquired RG-33's. For a SWAT team, the vehicle offers unmatched ballistic protection during high-risk warrant services or active shooter incidents. Its high water fording capability also makes it a valuable asset for flood rescue, as demonstrated during hurricane response operations. While the vehicles were transferred at no cost other than shipping, the operating costs shocked many departments. A single tire can cost over $1,000. An oil change requires gallons of synthetic oil. Electronic failures require specialized diagnostic tools that local mechanics do not possess. The sight of 30-ton mine-resistant war machines on American streets sparked a fierce national debate regarding the militarization of police. Critics argued that the presence of such vehicles escalated tensions during protests and fundamentally altered the relationship between police and the community, turning peace officers into occupying forces. Conversely, proponents argued that in an era of high-powered rifles and mass shootings, officers deserved the same level of protection as soldiers. The RG-33 stands as a monumental example of rapid industrial response to a tactical crisis. It was a vehicle designed with a single overriding purpose: to ensure that a mine blast was a maintenance event rather than a mass casualty event. In this regard, it was an unqualified success. It saved thousands of lives, allowing soldiers to walk away from explosions that would have disintegrated a Humvee. However, it was also a vehicle of compromise. It traded mobility for survivability, efficiency for protection, and maintainability for speed of deployment. It was too heavy for the mountains of Afghanistan, too wide for the alleys of ancient cities, and too complex for the average motor pool to keep running without civilian help. Yet for the soldiers who rode inside its V-hulled belly, listening to the drone of the tires and the hum of the jammers, The RG-33 was more than a truck. It was a promise, a 29-ton guarantee that no matter what was buried in the dirt ahead, they were coming home. It remains a flawed, frustrating, magnificent beast of burden, the iron fortress that drove straight through the fire.